of these hard and soft concept, hard and soft acid base concept. So we will see first classification of Levy's acids and bases. So first of all we will see the Levy's bases. Levy's bases. So these acids and bases can be classified into three categories: the hard, then borderline, and soft. So these are three categories we are considering for the hardness or softness of these Levy's acids and bases. So first of all we will see this Levy's bases. So if we consider the first element of the periodic table, which is hydrogen, and Levy's base of this hydrogen element is H minus. So this H minus is grouped into this soft category, that is H minus. So we are discussing here only the Levy's bases. Now the next element, the Levy's bases first. So we will see next to this H minus. The Levy's bases are considered from halide families, that is F minus, Cl minus. So these are the two anions which are placed in this hard category. Next is Br minus, we can consider, and here I minus comes under this category of soft bases. Then next is next to halide in the periodic table towards left is the group of oxygen. Group means oxide oxygen family. So the ligand, these bases containing oxygen as donor element are taken here. So in this case we have taken the halides as donor element groups or species. So next is oxygen containing, that is H2O. Then next stage is OH minus. OH minus. Then next is O2 minus. Then next is, so UD means all such oxygen donor atoms which are present in these groups are grouped into hard category. Then below oxygen in the periodic table, that is family of oxygen, next is sulfur. So that is placed here in this soft category, that is H2S, H2S, then OS, SH, then SH minus, then S2 minus, S2 minus. Then next to oxygen, the relatively next element is taken as the oxygen. Also, means we are considering other species of oxygen in which the substituents are generally R groups, that is alkyl or aryl groups. So on that basis we are considering this R, OH, then RO minus, RO minus, then R2O, R2O, and CH3, COO minus. So here RSH, RSH, then RS minus, RS minus, then R2S. So these are containing sulfur as donor atom, and these are containing oxygen as donor atom. So oxygen is harder species than S. So that is why we have placed this species under soft category and these species under hard category. Now next is the elements the species containing nitrogen specifically, that is NO3 minus, then ClO4 minus, then these are hard species, and in borderline category we have NO2 minus and N3 minus. N3 minus. In soft category, the nitrogen species, or specifically these are again soft species such as SCN minus, then Cn minus, then R and C minus, and carbon monoxide CO. Then next is carbonate CO3 2 minus, SO4 2 minus, SO4 2 minus, PO4 3 minus. Then next is SO3 2 minus, which is borderline species. Then S2O3 2 minus, which is softer species. Then next is NH3 and alkyl substituted amines, that is RNH2, then N2H4, then C6H5 NH2, C5H5N, and N2 and N2. Then under soft category, the species are R3P, phosphorus compounds, similarly RO thrice, RO3P, then R3AS, then C2H4 and C6H6. So these are organic species which are containing pi bonds or pi electrons, are also coming under this soft category. So here you will find that the R groups which are attached to nitrogen, that is alkyl groups, and there are the aryl groups which are containing pi bonds, but this R is not containing pi bond, that is methyl, ethyl, etc. So these are electron supplying groups, so they will increase the more availability of electron pair on this nitrogen. So they are harder species. But here the pi electron cloud attracts the electron pair on this nitrogen. So therefore these are relatively less hard species. And again here this species R3P, here it contains phosphorus, which is below this nitrogen in the periodic table. So these are also more soft species. Here AS, the P. So these are indicating that these are softer Levy's bases. So this type of classification will help us to interpret various reactions and which are active groups in the organic synthesis or organic reactions or inorganic reactions. Then we will see the next classification in which we are considering the Levy's acids. This is about Levy's acids. We will consider the Levy's acids such as, which are hard species, such as H plus, then Li plus, Na plus, K plus, etc. So these are hardness species. This is because their electronic configuration is similar to the earlier inert gas element, and therefore these are hardness species. Then there are next elements of these are alkali metals, and alkaline earth metals are also of same category. That is Be 2 plus, Mg 2 plus, Ca 2 plus, Sr 2 plus. Then next is these are Bf3. So Bf3, BCl3, then BOR3. Then here in borderlines it is BCH3 thrice. Then here it is BH3, then TL plus, then TL3 plus, that is TLCH3 thrice. So these are alkali metals, these are alkaline earth metals, and their electron shell is compact, and therefore these are having high polarizing powers, and therefore they are included in this high category. Now here BF3, BCl3, these are having boron, and you will find that these are electron deficient species also. Boron is electron deficient. This electron deficiency of boron is again pronounced because of this strongly electron attracting species like fluorine. Fluorine is electron attracting species. So the electron density of fluorine is decreased. So boron becomes more hard species. It needs electrons. Similarly, BCl3. Here chlorine is also harder species, Cl minus, and this chlorine also withdraws electron density from boron, so it is also hard. Then BOR3, here oxygen is also electron attracting group, so it also removes electron density from boron, and therefore it is hard species. Here you will find that CH3 is electron supplying species to very small extent. So the electron density of boron is slightly not that much, means compared to this, the electron density is not that much. Here means CH3 will shortly or in small quantity it will supply electrons to this boron. So electron density is not that much removed like these species. Now in this case hydrogen, this CH3, and this is also Tl3 plus is already we have seen already in previous discussion that Tl3 plus, Tl1 plus, these are softer species. So because of this CH3, it becomes again softer. Then next is aluminium. So if we consider aluminium 3 plus harder, Al CH3 thrice, then AlCl3, then AlH3. These are also harder species. Then we will see the next harder, that is Cr 3 plus, Mn 2 plus, Fe 3 plus, Fe3 plus, then CO 3 plus. So these are heavy species in higher oxidation states, and that is why the d electrons are not really available for bonding in pi orbitals. So these are having greater hardness. Then such species in their lower oxidation states are less hard, so they are grouped under this borderline and soft category. So we mark these as Fe2 plus, then CO2 plus, Ni2 plus, and Cu2 plus, then Zn2 plus, Zn2 plus. So these are borderline species. Now there are softer species like Cu plus, lower oxidation states, Ag plus, Au plus, Cd2 plus, Hg2 plus, Hg2 plus, then Hg plus, then CH3Hg, then COCl5, COCl5 3 minus, then PD2 plus, PD, PT2 plus, PT4 plus. These are platinum ions. So this is about the subspecies. Now we'll see next ladies hard acids. So these are the ions with oxidation state 4 or more, 4 or higher oxidation. Then these are your HX, that is hydrogen bonding species or molecules. So here we will have the RH 3 plus, IR 3 plus, Ru 3 plus, then osmium 2 plus. Then here we have Br 2, I2, and metals, that is M with the zero oxidation state and lower oxidation state with zero oxidation. Then pi species, pi acceptors. For example, trinitrobenzene, quinolenes, etc. or tetracyanoethylene. So these are pi acceptor species. So which are having much more soft. So any metal in zero oxidation state or such species like lower oxidation states are called soft Lewis acids. So on this basis, we will see the interpretation of various behaviors of these Lewis acids and bases. So we will see the behavior. So we have seen already that the halides are having varying hardness, that is F minus, Cl minus, Br minus, I minus. So these are the species having their hardness. So this is hard. So this is hard. So the hardness decreases, and in this case it is the soft. I minus is soft species. Then you will find that the hardness is decreasing in this order because the F minus is smaller in size, Cl minus is relatively larger in size, Br minus is also larger. So size increases in this direction and softness also increases in this direction. So in this way you will find that the degree of decreasing or increasing hardness or softness. So if you consider the number of electrons, the electrons present in F minus are few, and these are having nearest inert gas configuration. So as the electron cloud becomes bulkier and bulkier, the polarizability of the species also again increases, and that is why such species becomes softer and softer. Next example, if we see the oxygen and sulfur, if we compare the hardness of Levy's basis, that is O2 minus and S2 minus, then we find that here oxygen is a hard species and this is soft species. This is because the oxygen is smaller in size, sulfur is larger in size, and that is why it is less polarizable and where it is more polarizable. So this electron cloud is bulkier and therefore it can be easily polarized. The number of electrons, if we compare, it is having less electrons, it is having more electrons. Then if we consider another species example, if we consider S2 minus and Cl minus, S2 minus and Cl minus. Here S2 minus is soft and this is hard. Yeah, in this case you will find that there is not much difference in atomic number, but the nuclear charge makes the great difference. So if you find that the number of electrons are 18, here the electrons are also 18, means with respect to electrons, the electrons are same, number of electrons are same in both species. But there is difference with respect to nuclear charge. So here you will find that sulfur has nuclear charge here 17 and here it is 18. Nuclear charge is like this. It is 16, not 17, 16 and 17. So in this case, even though the number of electrons are same, the nuclear charge is small. So these electrons are relatively loosely bound. And here the nuclear charge is more. So same electrons are there. So these electrons are pulled closer to the nucleus. So these are strongly bound to the nucleus. And that is why it is hard and this is soft. Here we have to remember that the hard combination is preferred. Similarly, soft combination is preferred. But the hard and soft combination is not preferred. So we will consider some examples in which the behavior is observed to be different. If we consider the question like this, which of OH minus or S2 minus, OH minus or S2 minus, means which of these forms insoluble salts with +3 oxidation state transition metals. So transition metals with higher oxidation states are harder species. Transition metals with higher oxidation state are harder species. So they will react more preferably with OH minus and not with this, because here OH minus is hard and this is soft and these are also hard. So here hard combination is preferred. So the OH minus shows the formation of insoluble compounds because this is more preferred combination. So harder combination is preferred, therefore the resulting species is insoluble. And if we consider the reaction with sulfur S2 minus, the resulting species is relatively more soluble. So next question will be like this: will copper react more strongly with OH minus or NH3? Will copper 2 plus, we are having copper 2 plus. So you know that copper 2 plus is a soft species. And we are considering its reaction with OH minus and S2 minus NH3. Then it shows that comparatively, so here OH minus is more hard. This is more hard and this is less hard. Species. So copper being soft, it will prefer to react with NH3 than that with OH minus. Again, if we consider another Lewis basis of O2 minus and S2 minus, O2 minus and S2 minus, here again oxygen is harder species and this is soft species. So soft combination is preferred and hard soft combination is not giving stable species. Then we will consider third case, that is, will Fe3 plus react more strongly with OH minus or NH3? So we are considering here Fe3 plus, and this Fe3 plus is harder species. This is harder species, and we are considering its reaction with OH minus and NH3. So we have seen that this is more hard. So if we write here in comparative form, so that will be that. NH3. So hardness, these are both hard species, but OH minus is more hard than NH3. So Fe will prefer to react with this OH minus than NH3. But reaction is also possible in both cases. These products are easily obtained, but formation of OH minus is much better with Fe3 plus. Then we will consider another example, that is O2 minus and S2 minus. Similarly, O2 minus or S2 minus. In this case also, O2 minus is more hard than S2 minus. So Fe will prefer to combine with O2 minus and not with S2 minus. But this Fe can also react with S, but the stability is less. Then if we consider another example, will Ag plus react strongly with Ag plus reacts strongly with NH3 or pH3? NH3 or pH3. So here you will find that this Ag plus is soft species, and here you will find that this is NH3 is hard and this is soft. So you will find the better reaction between these two species. So Ag plus will prefer to form the stable compound with pH3. Then if you consider another example, will Fe2 plus or Fe3 plus react more strongly with CO? So here Fe2 plus or Fe3 plus will form So if we consider here CO, this carbon monoxide, this is a soft species. And here if we consider Levy's acids, so this is Levy's base. And if we consider Levy's acid such as Fe and Fe3 plus, then you will find that here that Fe is softest one. So if you will prefer to combine with CO because it is softer combination. So these are, and the degree of hardness we can compare. The hardness is like this, hardness. So Fe3 plus is more hard than Fe2 plus, and Fe is soft. So FeHCO will give us more stable complex. So similarly, we can have another example such as ZnO. We can have another example such as zinc oxide, ZnO, plus we will consider another compound, that is C4H9, C4H10. So it will give us the C4H9, it should be C4H9. Then it will give us the Zn, C4H9 plus this LiO, twice LiO. So here you will find that the Zn2 plus is soft species and this is hard species. Lithium plus is hard, this is soft. So hard combination will take place. So here the combination is hard, this is soft. So in this way we can interpret variety of reactions on the basis of this hardness and softness of Levy's acids and bases. So we will stop our discussion here. Please subscribe to this channel and press bell icon and like button. So thank you very much for watching this video.